Hello and welcome. Our topic today is Arab mathematics. The period covered is easy to describe. It stretches from the end of the 8th century to about the middle of the 15th century. Giving a description to cover the mathematicians who contributed, however, is much harder. However, certainly not all the mathematicians included were Muslim. Some were Jews, some Christians, some other faiths. Nor were all these mathematicians Arabs, but for convenience, let's call our topic Arab mathematics. The regions from which the Arab mathematicians came was centered on Iran-Iraq, but varied in military conquest through the period, as you can see by the map. At its greatest extent, it stretched to the west through Turkey and North Africa, to include most of Spain, and to the east as far as the borders of China.
There is a widely held view that after a brilliant period for mathematics when the Greeks laid the foundation for modern mathematics, there was a period of stagnation before the Europeans took over where the Greeks left off at the beginning of the 16th century. The common perception of the period of 1,000 years or so between the ancient Greeks and the European Renaissance is that little happened in the world of mathematics except for some Arabic translations of Greek texts were made which preserved the Greek learning so that it was available to the Europeans at the beginning of the 16th century. Many of the ideas, which were previously thought to have been brilliant new conceptions due to European mathematics of the 16th, 17th, and 18th centuries, are now known to have been developed by Arabic Islamic mathematicians around 4th centuries early. The background to the mathematical developments, which began in Baghdad around 800, is not well understood. This period begins under the Caliph Harun al-Rashid, the fifth caliph of the Abbasid dynasty, whose reign began in 786. He encouraged scholarship, and the first translations of Greek texts into Arabic, such as Euclid's Elements by al-Hajjaj, were made during al-Rashid's reign. The next caliph, al-Ma'mun, encouraged learning even more strongly than his father, al-Rashid. He set up the House of Wisdom in Baghdad, which became the center for both the work of translating and research. Al-Kindi, born 801, and the three Bana Musa brothers worked there, as did the famous translator Hanan ibn Ishaq. Perhaps one of the most significant advances made by Arabic mathematics began at this time with the work of Al-Khwarizmi, 1790 to 1850, namely the beginnings of algebra. It is important to understand just how significant this new idea was. It was a revolutionary move away from the Greek concept of mathematics, which was essentially geometry. Algebra was a unifying theory which allowed rational numbers, irrational numbers, geometrical magnitudes, etc., all to be treated as algebraic objects. It gave mathematics a whole new development path, so much broader in concept to that which had existed before, and provided a vehicle for future development of the subject. Another important aspect of the introduction of algebraic ideas was that it allowed mathematics to be applied to itself in a way which had not happened before. Now let's introduce some other important Arab mathematicians. I'll be shortening the names and trying to pronounce them as correctly as possible. We'll start with Abu Kamil, who was born in 850 and died around 930. He is sometimes known as Al-Hasib, and he worked on the integer solutions of equations. He also gave the solution of a fourth degree equation and of a quadratic equation with irrational coefficients. He lived after Al-Khwarizmi, and his biggest advance was in the use of irrational coefficients. Next is Abdul Hassan Kateb, 826 to 901. He was a native of Haran and inherited a large family fortune, which enabled him to go to Baghdad, where he obtained his mathematical training. He returned to Haran, but his liberal philosophies led to a religious court appearance when he had to recant his heresies. To escape further persecution, he left Haran and was appointed court astronomer in Baghdad. Tibet generalized Pythagoras' theorem to an arbitrary triangle. He also considers parabolas, angle trisection, and magic squares. Also, he was the founder of the school that was translated works by Euclid, Archimedes, Ptolemy, Eutychius, and Diophantus, and Pappus. which were unknown to the Arabs until the 10th century. Without his efforts, many more of the ancient books would have been lost. Perhaps the most impressive of his contributions to amicable numbers is that two numbers who are each the sum of the divisors of the other. We'll move on to Abdul Wahab. Abdul Wahab translated and wrote commentaries since lost on the works of Euclid, Diophantus, and Al-Khwarizmi. For example, he translated Arithmetica by Diophantus. He is best known for the first use of the tangent function and compiling tables of sines and tangents at 15-minute intervals. This work was done as part of an investigation into the orbit of the moon. His trigonometric tables are accurate to 8 decimal places, while Ptolemy's were only accurate to 3 places. Abu Bakr, right around the early 11th century, he was an Arabic disciple of Diophantus without Diophantine analysis. He gave a numerical solution to equations in the form of ax to 2n plus bx to n equals c, and only positive roots were considered. He also proved that 1 to the third plus 2 to the third all the way up to 10 to the third is equal to 1 plus 2 plus 3 plus 4 all the way up to 10 squared, in such a way that it was extendable to every integer. The proof is interesting in the sense that it uses the 2 essential steps of mathematical induction. This is the first known proof. Al-Kharji's mathematics, more than most other Arab mathematics, pointed in the direction of Renaissance mathematics. Next we have Omar Khayyam, 1048 to 1122. We won't go into his full name. A literal translation of his name meant tent maker, and this may have been his father's trade. He was a poet as well as a mathematician. He discovered a geometrical method to solve cubic equations by intersecting a parabola with a circle, at least in part. These methods have been described by earlier authors such as Abu al-Jud. He was an outstanding mathematician and astronomer. His work on algebra was known throughout Europe in the Middle Ages, and he also contributed to a calendar reform. He refers in his algebra book to another work of his which is now lost. In that lost work, he discussed Pascal's triangle, but the Chinese may have discussed the triangle slightly before this date. The algebra of Khayyam is geometrical, solving linear and quadratic equations by methods apparent in Euclid's Elements. He also gave important results to the ratios, giving a new definition and extending Euclid's work to include the multiplication of ratios. He poses a question of whether a ratio can be regarded as a number, but leaves the question unanswered. He is famed as a poet. His fame as a poet caused some His fame as a poet has caused some to forget his scientific achievements, which were more than substantial. We'll finish up with Al-Kashi, 1390 to 1450. He calculated pi to 16 decimal places and considered himself an inventor of decimal fractions. In fact, he gives 2 pi as 6.283.185.307.179.5865, which was the best until around 1700. He wrote The Reckoner's Key, which summarizes arithmetic and contains work on algebra and geometry. In another work, Al-Kashi applied the method now known as a fixed point iteration to solve a cubic equation, having a sine of 1 degree as a root. He also worked on solutions of systems of equations and developed methods for finding the nth root of a number, Horner's method today. Al-Kashi, Arabic mathematics, closes. After Al-Kashi, Arabic mathematics closes, as does the whole Muslim world, but scholarship in Europe at this time was on the upswing. Now let us turn to the different systems of counting, which were used around the 10th century in Arabic countries. There were three different types of arithmetic used around this period, and by the end of the 10th century, authors such as al-Baghdadi were writing texts comparing the three systems. Number one, finger reckoning arithmetic. This system derived from counting on the fingers with the numerals written entirely in words. This finger reckoning arithmetic was a system used by the business community. Mathematicians such as Abu Wafa, born around 940, wrote about this system. Number two, sexagesimal system, the second of the three systems, with numerals denoted by letters of the Arabic alphabet. It came originally from the Babylonians and was most frequently used by the Arabic mathematicians in astronomical work. The third, the Indian numeral system. The third system of arithmetic of the Indian numerals and fractions with the decimal placement value system. The numerals used were taken over from India, but there was not a standard set for the symbols. Different parts of the Arabic world used slightly different forms of the numerals. At first, the Indian methods were used by the Arabs with a dustboard. A dustboard was needed because the methods required the moving of numbers around in the calculation and rubbing some out for the calculation as the calculation proceeded. The dustboard allowed this to be done in the same sort of way as one uses a blackboard today. However, Al-Uqdisi, born around 920, showed how to modify the method for pen and paper use.
Here is an example of an early form of Indian numerals being used in the eastern part of the Arabic Empire. It comes from a work of Al-Shizi, not an original work by him, but rather the work of another mathematician, which Al-Shizi copied at Shiraz and dated his copy 969. The numerals had changed their form somewhat 100 years later when this copy of one of Al-Biruni's astronomical texts was made. Here are the numerals as they appear in a 1082 copy. A closer look will show that between 969 and 1082, the biggest change in the numerals was the fact that the 2 and 3 had been rotated through 90 degrees. There is a reason for this change, which came about due to the way the scribes wrote, for they wrote on a scroll which they wound from right to left across their bodies as they sat cross-legged. The scribes, therefore, instead of writing from right to left, the standard way that Arabic was written, wrote in lines from top to bottom. The script was rotated when the scroll was read, and the characters were then in the correct orientation. Here is an example of how the text was written. Because scribes did not have much experience at writing Indian numerals, they wrote 2 and 3 the correct way round instead of writing them rotated by 90 degrees, so that they would appear correctly when the scroll was rotated to be read. Here is an example of what the scribe should write. And here is an example of what the scribe actually wrote. The form of numerals in the west of the Arabic Empire look more familiar to those using European numerals today, which is not surprising, since it is from these numerals that the Indian number system reached Europe. Al-Banna, he gave this form of the numerals in his practical arithmetic book written around the beginning of the 14th century. He lived most of his life in Morocco, which was in close contact with Al-Andalus or Andalusia, which was the Arab-controlled region in the south of Spain.
It was the third system of calculating which allowed most of the advances in numerical methods by the Arabs. It allowed the extraction of roots by mathematicians such as Abu Wafa and Omar Khayyam, born about 1048. The discovery of the binomial theorem for integer exponents by Al-Kharajhi, born 953, was a major factor in the development of numerical analysis based on the decimal system. Al-Kashi, born around 1380, contributed to the development of the decimal fractions, not only for approximating algebraic numbers, but also for real numbers such as pi. His contribution to the decimal fractions is so major that for many years he was considered as their inventor. Although not the first to do so, Al-Kashi gave the algorithm for calculating nth roots, which is a special case of methods given many centuries later by Ruffini and Horner. Although the Arabic mathematicians are most famed for their work on algebra, number theory, and number systems, they also made considerable contributions to geometry, trigonometry, and mathematical astronomy. Ibrahim, born 908, who introduced a method of integration more general than that of Archimedes, and Al-Kuhi, born 940, were leading figures in a revival and continuation of Greek higher geometry in the Islamic world. These mathematicians, and in particular Al-Haytham, studied optics and investigated the optical properties of mirrors made from conic sections. Omar Khayyam combined the use of trigonometry and approximation theory to provide methods of solving algebraic equations by geometrical needs. Astronomy, timekeeping, and geography provided other motivations for geometrical and trigonometrical research. Sinan and his grandfather, Thabit, both studied curves required in the construction of sundials. Abu Wafr and Abu Mansur both supplied spherical geometry to astronomy and also used formulas involving sines and tangents. Al-Biruni used the sine formula in both astronomy and in the calculations of longitudes and latitudes of many cities. Again, both astronomy and geography motivated Al-Biruni's extensive studies of projecting the hemisphere onto the plane. Thabit undertook both theoretical and observational work in astronomy. Al-Batini, born around 850, made accurate observations which allowed him to improve on Ptolemy's data for the sun and the moon. Nasir Tusi, born 1201, like many other Arabic mathematicians, based his theoretical astronomy on Ptolemy's work, but Al-Tusi made the most significant development to Ptolemy's model of the planetary system up to the development of the heliocentric model in the time of Copernicus. Many of the Arabic mathematicians produced tables of trigonometric functions as part of their studies of astronomy. These include Beg, born 1393, and Al-Kashi. The construction of the astronomical instruments such as the astrolabe was also a speciality of the Arabs. Al-Mahani used an astrolabe, while Ahmed, born around 835, and Al-Kazim, born 900, Sinan, Al-Kuhi, Abu Masa, born 965, and Al-Biruni, and others all wrote important papers on the astrolabe. Sarif Tusi, born 1201, invented the linear astrolabe. In conclusion, the Arab Empire established across Persia, the Middle East, Central Asia, and North Africa, Iberia, and parts of India, from the 8th century onwards, made significant contributions to mathematics. They were able to draw on and fuse together the mathematical developments of both Greece and India. A golden age of Arabic science and mathematics flourished throughout the medieval period from the 9th to the 15th centuries. The House of Wisdom was set up in Baghdad around 810, and the work started almost immediately on translating the major Greek and Indian mathematical and astronomy works into Arabic. Recent research paints a new picture of the debt that we owe the Arabic/Islamic mathematics. Certainly, many of the ideas which were previously thought to have been brilliant new concepts due to European mathematicians of the 16th, 17th, and 18th century are now known to have been developed by the Arab Islamic mathematicians around 4 centuries earlier. In many respects, the mathematics studied today is far closer in style to that of the Arab Islamic contribution than to that of the Greeks.